Hi, everyone. I'm really happy to be here. I was looking at the presentations by name, and the last time I made a presentation here was in NANOG 23. I think that's before the internet was invented, but it was a while ago. So many thanks to the committee and to Sean for inviting me. So I'm going to talk about self-driving networks, and I want to start off by saying this is an idea in really an early stage. It's more conceptual. It's really about taking automation to the next level. There've been a lot of work around this. For example, we talk about zero-touch provisioning. We talk about self-organizing networks, especially on the mobile side. We talk about a number of things, but I want to bring everything together and really solve the problem of running a network. It's not a one-time, can I provision a service and can I do that more easily, more automatically? Can I have a push-button approach to configuring the network? Those are all good, but I really want to get beyond that to a point where the network just runs itself. So I'd started this about a little more than a year ago, talking about a completely self-driving, fully autonomous network. And so I drew an analogy with the car, the self-driving car, and the effort that got the self-driving car underway, as well as where we are today. So the question I want to pose is, how do we do the same for the network? So the self-driving car journey basically started in 2004 with a DARPA grand challenge. DARPA came up with this idea that let's build a fully autonomous vehicle, and let's not just talk about it, let's prove it. We'll take this freeway in Southern California, it was I-15, we'll block off 150 miles, 240 kilometers, and see if we can have cars drive themselves across that. There'll be no human drivers, there'll just be the robotic drivers. And so that was the challenge. And actually in 2004, nobody made it. And so they redid the challenge in 2005, and there was about 25 teams, and 5 or 6 of them made it. And then they redid the challenge in 2007, and in 2007 it was called the Urban Grand Challenge. And in 2007, they basically said, let's drive in an urban environment with human drivers, following the laws, the traffic laws. You've got stop signs, you've got traffic lights, so the car has to recognize all of that and do the thing. And that was a 96-kilometer course, and again, several teams made it. So the point is, they put out this grand challenge in 2004, and while they failed that year, in 3 years, they actually had something that was a reasonable prototype running around, driving in, on surface streets. What we have today is this unnamed car. I'll leave you to guess where it's from. But this is a completely self-contained vehicle, in the sense that there's no steering wheel, there are no brakes. You get in there and you say where you want to go, and it'll take you there. And it has a top speed of 40 kilometers. I don't know if that's imposed by the software, but that's kind of the constraint. But it will drive regular streets. It will deal with pedestrians. It'll deal with traffic lights. It'll deal with everything. It's in my neighborhood, so I see it usually several times a day, which is how I got to thinking about, if they can do it, why can't we? So what would a self-driving network do? Ideally, it would do everything that a NOC does today. So it would basically take a high-level guidance from a network operator saying, this is the kind of services I want to have. These are the customers that I prefer. These are the customers that should have special treatment because of various reasons. And then it would self-discover all its parts. It would organize and configure them. It would figure out when someone wants service. It would provision that appropriate service. It would monitor itself using probes to know whether the network is running and whether the service is doing well. And then it would, if it finds something wrong with a service or the service is suboptimal, it would do what's needed to improve the service. It would self-diagnose, and in the end, it would report saying, this is how I'm doing, this is what happened today, or whatever. So it would basically do everything that a NOC does today. And the goal is that ultimately, every part of the network is operated by this thing. That's kind of a pipe dream, maybe, but you have to set a target, and this is basically what the DARPA guys did. The goal was not, can you just operate the gears well? We did that with automatic transmission. Or can you just drive in a straight line and just manage yourself within the lane? They said, no, we want self-driving. We want the whole thing. So whether it is self-driving networks or self-driving cars, there are these 5 technologies that I think are really important. The first is telemetry. You need to know what's going on before you can make useful decisions about the environment you're in. In the case of cars, it's who's around me, what's the traffic like, what's the end-to-end path look like, what's in my immediate neighborhood. You got to look at all this information. And in the networks, it's not a whole lot different. You need to know what your neighbors are doing. You need to know what the overall network is doing. You need to know this high-level guidance that you got, what services you should be provisioning, and then use that to make decisions about the network. The second thing is multidimensional views. It's not enough to have one view of the network, or for that matter, for a car. Today, at least, the cars are mostly two-dimensional. A few people get off the road in funny ways, but if you think about in the future, you have drones, you actually have to work in 3 dimensions, and actually 4, because you need to also think what happens in time. So this idea that you not only get telemetry from all these different sources, but you actually put them together in meaningful ways. You correlate stuff. The third is automation, and I don't want to downplay automation. Automation is huge. The self-driving car that Google/Waymo made, the original one was a Lexus, which they tricked out with all kinds of interesting stuff. But the one that I showed a picture of is an electric car. So they've tried to take a lot of the stuff out of the way. But if you don't have an electric car, you want to make a lot of the systems within the car automatic so that you don't have to worry about them. Declarative intent, I'll tell you what that means. And then I think the most important, the thing that we have to work on is decision making. So in a car, you have a lot of things, a lot of different kinds of telemetry. You have a tachometer, a speedometer, you have the gas gauge, you have tire pressure sensors. But more recently, you put a radar onto it. You put different things that help with a human driving the car. Basically, these all give the human an indication of how the car is going and give the human a chance to improve that, going the right way or check that the oil is, doing okay. Really, this is feedback for the human. And for the first time, when Google built the Lexus that they made into a self-driving car, they put this thing called a LiDAR on it. A LiDAR is essentially a light-based radar. And it has 16 or 32 lasers spinning around really fast, taking 1 million measurements a second, and gives you a very good sense of what's around you in 3D. Basically, you send a laser pulse out, you get a reflection and say, how far is something from me? So you know, you have a very good resolution of everything around you. And so you know what's next to you. You know the relative speed of the thing that's next to you. You know what's in front of you and behind you. And you really have a sense of what's going on. And I think this is the first example of telemetry that we've put on cars that is not for a human to consume. It's not for the human to drive better. It's for the car to drive itself. And my question to us, to the community is, what's the thing that we don't have in networks that might help us when we get to the self-driving network? We have lots of telemetry in networks. We know what routing is doing. We know what packets are doing. We know what flows are doing. But, hopefully we know what applications are doing and what customers are doing. But what is it that we're not thinking of that if we want the network to run itself, that we would need? The other thing about telemetry is in networks, it used to be very often that you have a pull model. So you go and ask a device, how are you doing? How full is your CPU, or how busy is your CPU? What's the traffic look like? And you keep doing this pull thing, basically SNMP gets. And that model was okay for a while, but if you really want high quality, real-time telemetry, you don't want to do it that way. And so we're looking at a different model where essentially you program the device with the kind of telemetry you want, the rate at which you want it, and maybe some things about it, like give me a high watermark, or give me all the data, or give me 5-minute averages or 5-second averages. And then that data keeps streaming out at you. And so whether you do it from the control plane or whether you do it from the line cards, from the data plane, the idea is to have these sensors all over the box and to program the sensor saying, turn on this sensor, send me this kind of data at this rate in this format. And then that data comes streaming out at you. So and then you can collect it, you can put it in a database, you can have a query engine, or you can have visualization. So you can see what's going on in your network. That's the first step, and I think this is a really important step. We collect stats about the network. We're not always anal about it. We're not sufficiently obsessive about it. I've looked at stats that I wanted to do some analysis on. A year's worth of stats, a month in the middle is just missing. And it looks like the collector stopped collecting and nobody actually noticed for a month. I looked at some of the numbers and they don't make sense. So we need high quality, high frequency stats. And to do that, I think we need to have them real time. We need it to be streaming, and we need it to be optimized for machines. We do a lot of stuff where we try to do it in ASCII, and we try to do it in a format that humans can consume. I think we need to do it in a format that machines can consume, pre-process, and then display it to humans in a way that humans can consume better. So maybe as graphs or as 3D visualizations. But that's just the first part. The next part is to have this telemetry in ways that you can correlate them. And so, again, we do a lot of this today, but I think we could do a lot more. So we do know, from a router's point of view, who are my neighbors, what are my links, what's going on them. But then I also want to know things like, if I have such and such kind of traffic, what would the exit point be? Which peer would it go to? And we do that. L1, L0, L1, layer 0, layer 1 devices, of course, exist and have telemetry, but often are invisible to layer 3, which is maybe a pity. Middle boxes do their best to pretend they're not there, which is another pity. But at the end of the day, we need to see all of this so that we can make sense of the network. But I think in the future, we need to think about how do we gather this information in a way that we can correlate them better? And how do we look at this information across layers in the network, across geographies, across time? And especially, the stuff that you can do across time, you can have a sense of what is the normal behavior, what is the normal pattern. So if a particular interface is putting out 7 gig, is that normal? Is that high? Is that low? That question doesn't really make sense. But if you say, what's the normal range for that interface traffic at 10 o'clock on Mondays? That question might make more sense. Or what is the behavior of the network towards the end of a quarter? Because a whole bunch of people are trying to get some stuff done at the end of the quarter. So I think we need to have this kind of not only high quality information, but the information that we can correlate and actually get stuff out of. So there was an ad on the TV yesterday, I won't mention who it was from, but basically they say we turn information into insights. We need to do that in the network. We do root cause analysis, so when you get 16 alarms go off, you say, okay, what really happened? And we typically do it with rule-based systems. And I think we might want to try to see if we can do machine learning for that and see if that will get us a better sense. So for the normal, simple failures, that might be, a rule-based system might be fine. But over time, we might want to use machine learning to gather syslogs from multiple devices, process them, and say, okay, this is what really happened. I mentioned time-based trending. So if I know what is the normal behavior, then I can find anomalies, or I can predictively change things in the network to accommodate an expected traffic burst. So it is important to do time-based trending as well. And it is really important to understand that often local decisions are impacted by the global state. Again, going back to cars, which freeway, I want to go to the airport, I want to get there fast, and I want to make a decision right now, which freeway should I get on, which lane should I be driving in, but I need to know the global state before I can take the local decision. So all of this is important. So just getting the telemetry is not the be-all, end-all. You need to be able to correlate it. You need to be able to make sense of it. This is an unknown operating system. Don't ask me whose it is. But the important thing here is automation is really important. I don't want to downplay automation, but I do want to point out that automation is when, instead of having to deal with devices one by one, a human can handle 50, 100, 10,000 devices. So to do that, I need a level of automation. I need the boxes to be able to give me a framework where I can interact with them in much better ways. I love the CLI, but the CLI is for very specific tasks on one machine. And you need a way to take that task that you're doing and do it across 50 machines or 100 machines, especially when the machines start looking different. They have different features, they're from different vendors, they're running different versions of the code. So a lot of the frameworks that you find on operating systems today, starting with netconf or restconf, whichever is your favorite, basically says the way you configure BGP is independent of the device that you want. Now, there may be some features that are available on a particular device or a particular version of code, but basically this is how you configure BGP, and it doesn't matter. And then there are other things that you want to do, like monitor the device or upgrade the firmware or whatever it is. So all these frameworks that you have on box, whether they're based on Ansible or Salt, Chef, Puppet, whether the underlying language that you use is Python or Ruby, fundamentally, they're trying to make managing these boxes easier. But I will come back to the fact that automation is sort of top-down, where a human is dealing with machines, hopefully many machines, and they're trying to deal with them more or less the same way. And it's a really important component, but I want to get to the point where the humans are not in the network, that basically they step away and the network runs itself. Declarative statement of intent. Intent has become a very popular word in networking today. And as an example, in a self-driving car, if it doesn't have pedals, it doesn't have a steering wheel, what can you do? Well, you get in there and you'll see a little, maybe a dashboard where you can enter your destination or maybe talk to it, and it says, okay, you want to go to the airport, I'll take you there. and it'll do everything from there on. So you speak at a very high level, you say what you want to do rather than how to do it, and the car will figure out how to do it. Now there is this next step that you can say, why even do that much? Why can't the car just talk to my phone and say, your next appointment is in this Starbucks, oh, should I say Starbucks or Pete's? In 15 minutes, I'll take you there. Or even better or worse, depending on your way of thinking, I know that every day at 8 o'clock, you pick up your daughter, take her to school, go to work, and so when you get in the car and it's 1 minute to 8, I'm going to say, do you want to go to school? And take you there, and then go from there to work. These are all possible. These are all potentially good. There's a huge amount of privacy concerns around it. Do you want your car spying on you and looking at your movements all the time? Is that a record that it keeps that can be subpoenaed or can be sent to an advertiser to monetize you in different ways? All the more so when it's not just a car, but it's the network. And so if you're gathering all this information about the network, and in the network you're saying, this is the normal behavior or this is the usual behavior of this customer or this app, and you gather that information, where does that take you? And I'll come back to that thing. But the idea that you work with the network at a much higher level, you basically, you say what you want rather than how to do it, which is not what we do today. I mean, to a very large extent, we keep talking about how to do it. We go out and get our CCIE or GNCIE and say, I'm an expert in telling this machine how to do things. That's great, but maybe that's not where we should be. So this is sort of a conceptual view of SDN. My interpretation of SDN, because when you talk about software-defined networks, I have no idea what you're talking about. But when you think about an SDN system as a compiler that takes a high-level definition of what you want and puts it down in low-level, whatever is needed for each device, that translation is, I think, what makes SDN interesting. I should say that when I picked the title of the talk and the title for this project, it was a deliberate play on SDN, because self-driving networks. I'm not so fond of them. So I should also say that for me, this way of doing things is reminiscent of Jean-Luc Picard, because what does he do? He says, number one, make it happen. And essentially, we should be able to do that to the networks. We should be able to say, this is what I want, make it happen. And instead, we are trying to make it happen day by day. The last piece I want to talk about is decision making. And in doing this self-driving cars, the team from Pittsburgh, from CMU, basically looked at, actually, I think all of them did the same thing. They looked at, should we use rule-based systems? Should we use machine learning? What should we do? How should we, once we have all this information in the car, how should it act on it? Rule-based stuff looks really easy, what they now call if this, then that. So if this happens, do this. If this happens, do this. And each rule individually is simple, but when you look at the aggregation of rules, it becomes really hard to manage. It becomes really hard to add new rules. It's just very cumbersome. But it is very predictable. Machine learning, which a lot of people think is the essence of artificial intelligence, can be really creative. You give it 1 million pictures of animals and you say, this is a cat, this is not a cat. And at the end of the day, it'll figure out what's a cat and what's not a cat and do it really well. And you can give it these strange, hairy dogs, and it'll still say, that's not a cat. It actually does as well as, or in some cases, better than a human in distinguishing cats from not cats. But then you try to ask, how did you come to this conclusion? And you have no idea. I mean, trying to debug or understand machine learning, the system works. You give it lots of new pictures and classify them really well. But nobody really knows how to understand how it got there. Nobody knows how to tweak it. So it can do some really important things. If you'd asked me a year and a half ago, when would a computer beat a professional Go player? I would have said 10, 15 years. Well, they did it last year. They did it again last week. And last year was 4-1, 5 matches against a 9-dan Korean player. And last week it was 3-0 against a 9-dan Chinese player, Kejie. So amazing progress in machine learning, amazing progress in this. So we should use it. But like I said, it can come to some strange conclusions, and so you can't leave it unsupervised, which is a pun. So you really want to maybe use a combination of machine learning and rule-based systems. So the National something Board of Transportation basically has 5 levels of self-driving, starting with nothing, and then going on to fully autonomous. So I'm trying to make a similar thing here, where if you think about running the network, you can start with a fairly manual operation. Hopefully that's not done very often anymore. The second step is getting all this data and visualizing it so you can make better decisions. The third step is that the machine helps you with analysis and prediction and says, this is what's going on in the network, this is what will be happening in a month or in a week or tomorrow. And fourth step is recommendation. Hey, I've done all this analysis, I've got all this sort of history. This is what I would do if I were you, or here's 5 things I might choose from. But the human would be left to say yes or pick one of the 5 things. And then finally, we can get to completely autonomous. And I think we should be very careful getting to fully autonomous. Yes, I talk about self-driving, but at the same time, I am a little careful about this. I think as technologists, we too often build technology that we don't understand what it'll do or what the impact will be. And then kind of too late, we try to retrofit stuff. So hopefully you guys are at least here. You use a certain amount of automation in your network, and you do a lot of visualization so you know what's going on. Ideally, you get to the stage where essentially humans and machines work together. So this is human augmentation rather than human replacement, where you can make much better decisions because the machine crunches tons and tons of data and comes out with a few things that it would suggest that you do. And then maybe at some point we get to a fully autonomous network. So how do we get this kicked off? So just like there was a grand challenge from DARPA, I think there should be a grand challenge for networking. Now, Juniper is not the best entity to kick off such a thing, but I think something like this should be done. And I'm hoping that at the end of this talk, we'll have some time for questions and discussion about this. I'll go through the slides, but I will say again, I'm putting this out as a thing that should happen, not a thing that Juniper will do necessarily. So we've seen what a self-driving network means, self-discover, self-configure, basically do everything that humans do today to run the network. Oh, yes, the prize. Yeah, it's not my problem. I'm not doing this grand challenge. But the result would be to take the tedium out of networking, to take some of the very manual, very repetitive tasks out of the network. And that's just the first step. The idea would be to free people up to do higher level tasks, to work on service design rather than figure out, okay, this person wants this pseudo wire, how do I provision it, and what's the command that I use on this box, what's the command I use on that box, how do I make sure it's all working? So to really, take that burden off the humans and allow them to work at a higher, more creative level. The other thing is agility. A lot of people talk about agility. I want to put new service in the network really fast. And actually, a large part of that is process, and a large part of the process is fear. If I did this, what would it mean? What would I break? If I made this change in the network, how would it go wrong. So, I'd like to get to the point where the network is doing a lot of these things. And, that fear factor has been removed because we've had that chance to do all this for a while. And even further, to become anticipatory, to get to the point where I know what the network will do because I've done this time-based trending. I know what this application is going to look for. I know what this human is going to do. And based on that, I'm going to prepare the stage before they do it. There's this whole sort of approach that we had towards improving how applications work in networks, essentially by saying, on the one hand, the network operator should know that there are these 10 applications that are in the network and define the QoS for them and put maybe ACLs or filters of some kind that say, I'm going to recognize this kind of application and I'm going to optimize it in the network, or I'm going to recognize some other application and make sure that they get expedited forwarding, whatever it is, right? And the idea that the application will work better because a network operator does a bunch of work just doesn't fly. The flip side of it is I should give APIs to the application writer to allow them to use the network better. And that doesn't fly either because the application writer wants to focus on his application, probably doesn't know what a network is and doesn't care because it's just, I send a packet and it gets there. And so maybe a third approach is the network is going to recognize these applications, going to see what's happening and say, hey, this application behaves in this way. I need to do this to make sure that it works well. Maybe some guidance from an operator that says, these are the important applications, do what you need for them, and these other ones don't matter as much. But having said that, rather than putting the burden on the network operator or on the application, have the network respond in real time by learning about these things. And maybe the most important is security. When you think about stuff that happens in networks, usually it's not really urgent. There are lots of important things you need to do. But even when there's a failure, you've built enough redundancy so there'll be another path through the network. But when someone is attacking you, you don't have time. You really want to be able to identify that really quickly, figure out what the mitigation should be, and put that in place. And so maybe security is one place where we can really use this power. So in the spirit of yet another expansion of SDN, we can call this self-defending networks. So challenge, I don't know. I mean, I picked one here, but the one that I'm more fond of is a self-driving edge network. Because the edge is where services are, whether the services are business customers, residential customers, mobile customers, or peering. That's where if you can do something that improves that service, your customers or your peers will feel that much, much more quickly. I do want to talk about the impact of this and potential possibilities. I think when we talk about new ideas, a grand vision or grand challenge, we should think about what is it that we can't do today or is really hard to do today that this would make possible. But from a very, very high level point of view, I'd like to look at this as a closed loop system where essentially at the bottom in this blue cloud is a network. You've got telemetry coming out of it in multiple buckets, a collector putting them all together, an entity doing analysis, at the end of that coming up with the decision and pushing an action back into the network. It is nearly closed loop. There is some guidance about, what things you want to accomplish, what things you want to optimize in the network, and that's coming from a human typically. We need standardized models for telemetry. When I talk about this real-time model-based streaming telemetry, we need models for that. So Juniper has a few models, but I think it needs to be something the community does. We have an open source collector, but again, this should be something that is taken up by the community and built on. Analysis, this correlation of data, we definitely need to do this. I think it'll vary a lot, but if we have common data models for the telemetry that we're collecting, it becomes easier. We need a set of actions that are standardized, and even more, we need to know how to translate those actions to stuff the box can do. And so here we have something. We have netconf that has been a standard in the ITF for a while, and there's now a lot of action in the ITF defining new data models for services, for configuration, even basic things like BGP and OSPF, ISIS. There is, of course, this whole separate thing called OpenConfig, driven by a number of providers, content providers and service providers. So I think of this whole thing, the action part is sort of the best defined from a standards point of view, but I think we need to make this whole thing standards oriented so that people ask, what if the network is multi-vendor? It should work. It might work better with some vendors than others, but it needs to be a multi-vendor situation. So there's your closed loop. So if we get there, yeah, you guys can all sit on the beach and sip a Mai Tai or whatever that rainbow-colored drink is. But it will involve some serious impact. Instead of being BGP geeks and I know how to tweak this policy to get this kind of routing, maybe I have to be a service designer or maybe I have to tweak the AI because it's not behaving exactly like I need it to. The other thing is, and there's this thing that James Hamilton said many years ago, the network is in my way. The idea here is the network gets out of the way. It does what it needs to do on its own. It anticipates what is needed in the future, and basically, slowly and slowly, you'll find that the network is not getting in your way. Or if it's getting in your way, it's because it's actually running out of resources, and it'll point you to where I need more interfaces here, I need more ports there, I need more lambdas there. SLAs are automatically met. The networks adapt, react to things that are happening. So you can do all this planning, but in a week, even in a day, sometimes the planning just breaks down because something happens that you don't anticipate. And the last thing is security becomes good guy bot versus bad guy bot rather than a human versus a botnet, which is no contest. So really you get to using AI in defense because the people doing the offense are using AI already. You notice that I didn't say AI a whole lot because I'm not doing this for technology. I want to make the operations of the network better, but I think AI/machine learning is important. Here's the minus side of this, that you could have the mad robot syndrome. You could have, when you do self-driving, you lose control, or you give up control. So I don't actually use cruise control a lot in my cars. I mean, I just don't like it. I have my foot hovering over the brake because I don't know what's going to happen. Now, maybe with this adaptive cruise control with radar, it might be better, but yeah, I'm a stick shift kind of guy. We software guys don't trust the hardware. We don't trust the software either. We don't trust anything. So you might want to go down the path of human augmentation rather than full autonomy, at least until you know that this thing knows what it's doing. I was in a friend's Tesla. I have a very, very low-end Tesla. It's called a Leaf. It doesn't have any self-driving. But I was in this friend's Tesla, and we were going about 25 miles an hour on a city street, and the lane split into two. And the Tesla decided to take the right lane, and a guy was entering off the parking lot into the right lane. The Tesla has 7 cameras on it, and it can't figure out that someone's trying to enter. And so my friend actually had to take over and jerk the wheel over. I mean, he was showing off about the Tesla, but he had his eyes on the road, and he jerked the wheel over. And so one of the things I'll say is I'm really, really high on machine learning. But the fact is, you have to give it 1 million pictures. You have to give it 1 million hours of driving. You have to give it 1 million this and 1 million that. And even 1 million is not enough. My daughter has just started driving about 4 or 5 months ago. She did 50 hours of driving. And while I won't tell her to her face, she's actually a pretty good driver. So I think we need to have this balance of, yeah, the machine will learn and the machine will help us a lot, but it needs to be in conjunction. There's this whole other problem of net neutrality, privacy, how much data should you gather, what can you do with that data, because all of this is driven off of data. And if I'm tracking an application's behavior or I'm tracking a customer's, subscriber's behavior, how far can I go and when is it too far? A huge other problem is this whole job loss thing. So, okay, I don't need as many knock operators. I don't need as many, people building cars. I don't need as many, whatever. Pick your favorite job. We're seeing job loss due to AI, due to automation. And it's a big issue. It's not something I would say we should, have legislation about and do protectionist stuff around. But it is something that we should think about, and it is something that we should actually focus on. So again, while I'm really high on the technology and while I'm really looking forward to having more of this and having the networks run much better, we should be aware of these issues and we should plan for them. I talked to NTT in 2015 that already started preparation for the 2020 Olympics. And they're the Japanese and they're very meticulous about these things, but preparing 5 years for this 2-week event seems a bit much. And maybe it's an exaggeration on my part. I'm sure there's a bunch of other things, but what if we could get to a point where, oh, wait, I forgot, the Super Bowl is tomorrow. I'm just going to dial up this thing. In fact, here it's not even a human doing it. It's a robot doing it, but that's maybe too much. But I'm just going to dial up. I'm going to have all this equipment shipped to the stadium, self-driving truck, of course. It gets out there. It self-organizes itself. It places itself all over the stadium. The event happens. A bunch of people here are really active on the net, so I put more networking resources here. On that part of the network, they're actually watching the game, which is a very strange thing to do at a stadium, but they are doing that. So I don't need as much. And so, this network is in real time self-organizing, adapting to behavior patterns. And then the event is over, it all goes back on the truck and goes to the next event, rather than having this really long planning cycle and trying to predict today what people will be doing 3 years from now in terms of how they interact with the network and stuff like that. So basically, this is just one crazy idea. But I think if we had a self-driving network, if we had networks that really ran themselves completely, we would approach building networks and running networks in a very different way, and we'd be able to do things that we couldn't do today. So that's pretty much it. I think there's this vision in front of us. There's an economic imperative to reduce OpEx, but not just reduce OpEx, but also make it much more effective, because we do a lot of work in the network on maybe not all the data, because humans are processing it. And if we actually did it with all the data we could get, we could do a better job. There's an efficiency imperative that we spin up and use resources as needed and in just-in-time manner, because we have really fast response as well as predictive analytics. We can use resources only when they're needed and turn them off. There's an agility imperative. All the service providers say we need to respond to things much, much more quickly, not have a 5 or 6 month planning cycle, but maybe do this in days or minutes. Or maybe even just have the machine do it, predict, analyze, and anticipate. And like I said, there's a security imperative, because when the bad guys are attacking, there is a real urgency in responding. And for all the big threats that have happened, the big data breach in Yahoo or Target, there were indications that something was happening. We just didn't, there were so many false positives, we couldn't focus on the true positives. And so can we have a machine help us with that? So, I mean, the call here is, we should, first of all, think about the idea in general. Should we have a self-driving network? But if we wanted to do it, what is it that we need to build? What are the standards that we need? What are the components? How do the different pieces work? And I think one very important thing is what part of the network do we start with? What's the moral equivalent of driving on a freeway with no human cars? That we can focus on, improve the technology, and then take it to the wider network. So that was my talk. I have time for questions. A moderator somewhere, but if you have questions, I have no answers, but feel free to ask.
So I'm Srinivas. I work for Microsoft. So I just have one comment on presentation. It's an excellent presentation and a great vision on the self-driving networking. I think embracing the machine learning is an excellent thing. I think from the Microsoft perspective, Microsoft, it's a well-known. AI and artificial intelligence and machine learning, it's Microsoft embraces across all the domains. That includes networking as well. So I just want to comment on one thing which you mentioned, like job loss and those things. I think just one analogy, when cars are invented, many people thought, okay, there is a job loss, horses are out of the job, and the people around who maintain the horses out of the job and those things. But in fact, actually, it didn't do that way. It gave an opportunity to build different skill set like cars repair and showrooms and marketing and all those. And it improved the job market in a different domain. In the same way, when we do a self-driving networking, we will get a different skill set. We need to get a different skill set. It may not be job loss. It may be a different skill set required for it. And that's what usually Microsoft publicly embraces about AI. Because of the AI, we lose a different skill set or jobs, but we need a completely different skill set that definitely benefits the humans as a population. So that's my comment. Thank you.
Thank you. Let me comment on both aspects. The first is I went to my first AI conference in December last year. And at this conference, there was a number of expected attendees, people from Google, Facebook, Baidu, and so on. But there were also a number of car companies. Audi was a gold or platinum sponsor. There were financial companies. There were companies from medicine, either radiology or gene discovery drug discovery, genetic analysis. So many, many different disciplines are using AI. So why not us? So I completely agree with that. The second thing is about job loss. I think it's a little bit different now. Back in the day, we built physical machines. So instead of building a house, instead of digging, humans digging, we got bulldozers, we got cranes. And so instead of 50 people building a house in 6 months, I'm just making up the number, you'd have 5 people building a house in 2 weeks. But there's a very big difference now because we're finding AI is taking or taking on cognitive jobs. There was a list, I think from NPR, of jobs that are safe if you're worried about AI and robotics, or if you're worried about job loss due to automation. And top of the list was elder care or nursing or stuff like that, social things. Well, we have social robots now. The Japanese are very focused on elder care because they have an aging population and a lot of technology and not a lot of immigrants. So I think the dynamics of job loss are really changing. And if you want to get really scared, read a book called The Rise of the Robots. I forget the author's name, but you can find it. So I'm not saying yes or no. I do agree that when you have job loss due to automation and the technology moving forward, it transforms after a short pain into a new set of jobs and new skills. And hopefully that will continue happening, but I wouldn't be sanguine about it.
Thank you for a wonderful talk, Matt Petak from Yahoo. Your little anecdote about driving down the street in the Tesla, I think is especially interesting in the view of self-driving networks. Talking about a network in isolation is one thing, saying I can put all the pieces together, build my AI, and let it run itself. The challenge is networks, by their very nature, don't tend to be isolated. Certainly in the industry we're working in, we connect to everything else on the planet. So do we get to a point, and does your vision encompass this won't be fully realized until the entire internet planet-wide is self-driving, or are we going to be sort of the first people out there doing self-driving networks, or like the poor guy in the Tesla going, damn it, all these other humans are really dangerous, would you stop trying to drive into me?
Yeah, so are we going to have the moral equivalent? Because people have suggested this. We have HOV lanes. Maybe we should have a self-driving lane and, take the humans out. No, we actually, in networking, we always have to coexist. And so even within an autonomous system, even within a single provider or even a part of a provider's network, you're going to have self-driving or self-drivable components, and you'll have non-self-drivable components, and you'll have to deal with them. But definitely, at the boundary of the network, you might say, my network is fully self-driving, but my peer isn't. We have to live with that. We have to build. We can't say, we flip a switch and the whole world becomes self-driving.
So from the job loss perspective, that could be a nice boundary for saying, okay, inside where it's safe, I'll let the AI do its thing, but where we have to talk to other human-run networks, yeah, we as humans will still interact there. Thank you.
Okay, thanks.
Hi, Simeon Mete from Berkeley Lab. I'd like just for a second to nitpick your analogy, but I promise there's an actual question in there. So taking this idea of taking the humans out of the HOV lane, that part of the analogy, I would point out that DARPA challenge was off-road, right? There weren't any roads. You have to have AI, at least you have to have computer vision for the machine to see, well, okay, there's a rock in the way, I need to drive around the rock. I kind of think if we were to build infrastructure for self-driving vehicles, that it would look a lot more like a railway. And maybe we wouldn't need AI because we wouldn't have to have cameras to say, where's the edge of the road? So my question to you is, how much do you think the complexity, the high OpEx part of operating networks is self-inflicted and could actually be fixed by just getting vendors to implement standards and methods that we don't need an AI to figure out how to operate the network?
So definitely a big piece of this is self-inflicted. It is self-inflicted in multiple ways. Yeah, I know part of it is the vendors, and we put a lot of knobs in there. Provider A wants these knobs, provider B wants a different set of knobs, provider C wants a different set of knobs. Provider D sees this whole set of knobs, like, where do I start? But the other part is, in networks, there's a lot of legacy. You guys probably remember what ATM is? I'm sure there's somewhere in your network there's an ATM circuit. And the problem is, if you look at the mega data centers, whatever you want to call them, they say, I'm going to build here's a row of servers, and there's going to be 10,000 servers, and they're all going to be the same, down to the capacitors and down to the version of Linux or whatever your favorite OS is. And now I'm going to do automation, and one push of one button, 10,000 things will dance all the same way. They do have legacy in a way, but they move forward very quickly, and they sort of cap and grow, and they're masters at that. And in the network, we don't quite do that. And also, a lot of the services that we provide are customized, especially to the bigger businesses. But we come up with all these different service definitions that make it harder to manage. From the point of view of coming down to standardization, I think people are moving to NetConf, and that I think will make life easier. Not everyone is there yet. And then everyone has their own automation infrastructure, and they're all different. And if we standardize that, that would help. But at the end of the day, that would ease the pain. Driving, I used to have a picture in my slide deck of the original, what was it called, Benz patent motor wagon, built 130 years ago. Very, very, very hard to drive. And we've come a really long way, even before self-driving. That's all good. And like I said, automation is really important. But it's not the end all. I think we can go beyond. And the car industry definitely has shown us that. So I think, there's definitely self-inflicted wounds. There's definitely, being a service provider, I have to provide service, and I want to customize the service, so that makes my pain higher. But there is a part of it which, can I actually get my hands out of the network, or can I operate at a much higher level?
Thank you.
Thanks.
So this is Yao-Qing Liu from Clarkson University. So in order to enable agile mobility and security, we know our current TCP/IP-based architecture has some drawbacks. So we know right now there are many proposed, we call it future internet architecture, such as named data networks or mobility first architecture.
Yeah.
So my question is, from your perspective, how would you see the potential of these architectures? Thank you.
It's a good and difficult question. I am a huge fan of named data networking. And in fact, I got our company to sponsor or be a member of named data networking, interact with the Park guys on CCNX. The problem is I don't know how to scale that. But also, at some level, they're really focused on the network as a provider of content. And then they think of everything in the network as being, me interacting with content. And I think we have other paradigms in the network, and you can try to squeeze them into the content box, and it kind of sort of works. And you might say content is 90% of it, and the rest doesn't matter as much. Fixing the underlying network, I think, would be helpful. I'm not saying that NDN or CCN is the answer, but fixing the underlying network would be helpful. This sort of patching security after the fact, trying to add security to the internet architecture has not been extremely successful. We're getting better. But at the end of the day, you'll still have a network that you have to manage. You'll still have devices. You'll still have people that want to come on and get a service. You'll have, the network will change. There'll be a surge of traffic because everyone wants to download Beyonce's latest CD or Adele's, if you prefer. So you will still have to manage the network. So having a better network infrastructure would help, but I don't think it would solve the problem of operating the network.
Thank you.
Thanks. Well, thank you, everyone.